Okay, this lesson's about expanding on knowledge that you already know. So, for instance, something like this, you should already be familiar with. We've covered this in the past, but it says that 5 and negative 5 are square roots of 25. Now, that's true. There are two numbers here that are technically square roots of 25. If I try to ask you, what the square root of 25 is, basically my question for you is what number do I square would equal 25? That's essentially what the question is when I'm asking the square root of 25. And the answer to that question is two numbers, 5 and negative 5. Because you could square both of them, and each of them would end up at 25. Positive 5 squared is 25, and negative 5 squared is also 25. So there's those two possibilities. So that's why there are two answers. Okay? We already know this. We wrote this back in the day that the square root of 25, we wrote it as positive and negative 5. Okay? Or you can write them separately. It doesn't make a difference. Writing them as 5 and a negative 5. Or writing them with the plus minus sign. But that's something we already know. We're going to expand on that a little bit today. So here we have 2 is the cube root of 8. So what that means is if you take the cube root of 8, basically when I'm writing this, I'm asking you this question. What number would I cube would equal 8? So that when you're trying to find a cube root of 8, that's essentially what you're asking yourself. Is what number can I take to the third power to equal 8? And the answer is only one number. It's just 2. So my question is, why is it just 2? How come it's not negative 2 as well? Kind of like, 5 and negative 5. Well, if you try to take negative 2 to the third power, you try to cube that, you actually get negative 8, because we're doing negative 2 times negative 2 times negative 2, which, if you multiply that all out, comes out to be negative 8. So negative 2 wouldn't work. It'd be giving me the wrong number, right? I want a number that's cubed that would equal positive 8. If I wanted the cube root of negative 8, then that would be negative 2. But still, it's only one answer. It's not 2. It's just that single digit. Right? And it can't continue this kind of philosophy. If we try to take the fourth root of 16, right? I'm essentially, again, asking you the question, hey, what number would I be taking to the fourth power would equal 16? And the answer to this one is that there are two answers again. It's 2 and negative 2. So why is it that when I have the fourth root, or the fourth power, or whatever, I get two answers, or two possibilities? When I take the square root, I have two possibilities, but when I take the cube root, I only have one answer. And that has to do with the fact that it's even or odd index, or even and odd root. So even roots will have essentially two possibilities, because, when you square something or take something to an even power, the negative version would end up canceling itself out and making a positive version anyway. Right? Because two negatives make it positive. Even if you have 4 of them, right, you still get another positive. So every time you have an even power, an even root, those negatives essentially will balance each other out and end up to be the same as the positive results anyway. So that's why it works. But when you take it to an odd number of powers, you get, a positive number with a negative number, and it always results as just a single negative. So you get different results there. You have, it could be positive or it could be negative. So that's why you can't really share them together. And you only have one answer rather than two. Alright? But let's start finding roots of these things. The calculator can do it, but let's talk about how many solutions that we're going to have. So this table sort of says everything that you need, especially kind of in this vicinity. But if you have an odd index, and by odd index I mean something like the cube root, or the 5th root, or the 7th root, etc. Anything with an odd index number, like 3, 5, or 7, or 9, or whatever, will have one real root, of course, and so only one answer, not two. Kind of like we saw that cube root of 8 in the last slide. Its only answer was 2. If I wanted to take the cube root of a negative 8, like I said, that answer would have been a negative 2. But it's still only one answer per question that I'm asking for. Okay, one real root. It's just, if it's a positive number here, your root is a positive number as well. If it's a negative number here, then your root is a negative number. That's for odd indexes. An even index with a positive radical, or radicand as it says, but the number inside the radical, would have two real roots, and we've already looked at that, like the square root of 25. It's an even index because it's technically a square root, right? And it had both positive 5 and negative 5, two real roots. So anytime you have an even index with a positive number on the inside, you technically have two real roots. And of course, even index but with a negative result. So for instance, the square root of negative 25. So it's an even radical because it is a square root, but it has a negative on the inside. This has no real roots because this technically has imaginary roots. We talked about that in previous videos as well. You can't take the square root of a negative number. You can't take any even index of a negative number. They would all be imaginary roots, but we're not going to talk about imaginary roots. We're just going to stick with the real roots today. Okay. According to the video. Oh, what's up?
I just thought you were talking.
Well, I am technically, but it's for the video.
Did I mess you up?
A little bit. That's all right. Alright, anyway, I can't edit that out, so we're going to continue. People think I'm talking to myself. Technically I am. Alright, radicand of 0. Basically what this says is if you have any root of 0, the 7th root, the 9th root, 8th root, etc., that your answer is going to be 0. So it doesn't matter if it's an even index, an odd index. If you take any root of 0, your only answer is ever going to be 0, which is kind of a common sense thing. That's what you would expect. So, anyway, let's go ahead and try a few of these out. Again, we're ignoring imaginary roots. Technically, imaginary roots are here, but we're only going to look at real roots. Okay, keep in mind, if you don't see an index number here, right, when you take the root of something, we're assuming it's the square root, or we're assuming, it's essentially 2. Okay, it's an invisible 2. We've mentioned that, I think, in the previous one as well. Alright, so let's figure out what the roots are here. So the 6th root of 64, which would look something like this. You'd be taking the 6th root, so 6 is your index number, of 64. My question for you is, how many roots is this going to have? Well, if you look at your table, right, this is an even index number because 6 is an even number. And I have a positive radicand, the positive number inside of it. So it's this guy. And it would have 2 real roots. Alright? Now, if you type this in your calculator, and to type this in your calculator, what you would do is you would hit, well, let me just go ahead and show you. Give me a second. Okay, you can see it's already there, but let me show you how to type it in. So if you hit 6, and then we go to the math button, and your calculator could vary a little bit from this one, but you hit 6 and you hit the math button, you'll see the 5th result is, it says x root. We're going to select that, because that basically means that we're going to choose the number for the root, which we already did. We hit 6, and now when I select that 5th option, let me get it. Then we're going to be taking the 6th root, so you'll see it'll make that 6th root there. It'll put that 6 in where that x was. And then you can type in your 64 and enter, and it gives you your answer. Now, of course, it says 2, the calculator's not going to tell us both numbers, but technically we already mentioned that there are 2 real roots here. It would be a 2 and negative 2. So you can try it if you wanted to, but 2 to the 6th power should equal 64, and negative 2 to the 6th power should also equal 64. So let's see that. Let's give that a try. 2 to the 6th power equals 64, and then in parentheses, negative 2 to the 6th power should equal 64 as well. So you see, you get those two roots, 2 and negative, 2 positive, negative. All right, but cube roots of negative 216. So this would be the third root, that's what a cube root is, of negative 216. So cube root, that's an odd root, right, because it's the third root. An odd index will always have one real root. So we're only going to have one answer here. And if you want to do the same thing and type this in your calculator, you'll see that your calculator will spit out and say that our answer is, what is it? Hold on, I think it's negative 6. But we can type that in and just double check ourselves. So if we do, let's go to the math button. We can hit the cube root, which is the fourth option, negative 216. I think it was what it was. Yeah, we get negative 6. So it's not positive 6 and negative 6, it's just negative 6. So you can try that as well. If you want to put negative 6 to the third power in your calculator, it'll get negative 216. But if you tried positive 6 to the third power, it would be a positive 216, which is not what we were asked to find. Right? We wanted the negative 216. Alright, so it only has one real root. That real root was negative 6. If you want to take the fourth root of negative 1024, alright, notice it's an even index, right? The fourth root, even number. And the inside is a negative number. So that's followed in this category. It's an even index but a negative radicand. So this would have 0 real roots. This is kind of like that square root of negative 25, you know, or has the imaginary numbers. This would have imaginary roots. But we're not going to worry about them right now. We're just going to worry about how many real roots it has. It has none, so let's continue our day. Alright. Just real quick, the fourth root of negative 256, that, again, an even index with a negative radicand. That's this guy. It would have 0 real roots. The sixth root of 1 is an even index with a positive radicand. So it would have 2 real roots. And you could probably honestly do this in your head. Those 2 roots would be 1 and negative 1. But your calculator could always do it for you as well. And the cube root of 125. It's an odd index, right? Because cube is the third root. Odd index, any odd index is going to have 1 real root. So this would have 1 real root. And if you're wondering what that root is, the calculator will tell you it's going to be 5. Okay, I'm going to skip that just for the sake of longevity of this video. Alright, let's talk about something else that we already know, but let's expand our knowledge on. Perfect squares. We already know perfect squares. You know, 1 squared, 2 squared, 3 squared. We know these numbers, and of course many, many more. Maybe even have them memorized. You know that 1, 4, 9, 16, 25, 36. These are perfect squares. Right? We use these a lot in math, so that's why it's really beneficial if you kind of like know them off the top of your head. But let's talk about other perfect numbers, like perfect cubes. We could even talk about things to the 4th power, those perfect, whatever you would call those. But let's just start with perfect cubes. Okay? I don't know this list off the top of my head, but I would know how to find them, because 1 cubed would be 1 times 1 times 1, which of course equals 1. So 1 is a perfect cube. Right? If you wanted to find others, you would just do 2 cubed, which of course is 8, 3 cubed, 27, 4 cubed, 5 cubed, and 6 cubed. You can make, obviously, you can go as far as you want. You can continue to go 7 cubed, 8 cubed, 9 cubed if you want to. But the trick is that you know how to find them, right? You know how to make this list even if you don't have it memorized, because it's going to be 2 times 2 times 2, 3 times 2 times 3, 4 times 4 times 4, you know, etc. So you can find that list of numbers even if you don't have them memorized. And the reason I'm bringing this up is because back in a couple weeks or months ago, we talked about simplifying radicals like the square root of 24. Now, it's real easy if the radical is a perfect square, but 24, as you can see on the list of perfect squares here, is not on that list. It is not a perfect square. So what we did is we said, okay, let's see if we can break it up and try to divide out a perfect square from it. So you would look at your list of perfect squares, and you would think, okay, and we're going to ignore 1 because dividing it by 1 would not do anything. But can I divide, is 16 go in 24? Is 24 divisible by 16? Or is 24 divisible by 9? Or is 24 divisible by 4? We would see all these possibilities and find one that worked. If you typed in the calculator 24 divided by 4, you would see, hey, I get 6. That perfect square would work, so we're going to use it. We're going to use that 4 and 6. Because 4 times 6 is 24. 4 is a perfect square, so it's nice and convenient for us. Now, we're using that because 4 being a perfect square is really easy to simplify. The square root of 4 is just 2, right? And a decimal is just a perfect number. That's the reason we used it. And then the square root of 6 is left as our remainder because it's still not a perfect square, but there's nothing we can do to simplify that to 6. So this is how we would simplify the square root of 24. We already know this process. We're going to repeat this process with perfect cubes. Okay, we've made this list of numbers, and we'll use it when simplifying now. So it's basically the same exact thing, but using a kind of a different set of numbers. So let me kind of write them back down. It was 1, 8, hold on. There's 1, 8, 27, 64, 125, and 216. That's as far as I got. You could get more if you needed more, if you think you needed more. But I want to take the cube root of 27, so we're going to repeat this process we just did with the square root of 24. Alright, so let's look at our list of perfect cubes and think, hey, you know, is 27 on that list of perfect cubes? Is it a perfect cube? And it is, right? So that means it should simplify really nicely. What is the cube root of 27? It's just 3. And that's because 3 cubed is 27. So it's a perfect cube. It simplifies real nice. I don't really have to do much more to it. Now, number 2 is a little different, the cube root of 54. Because if we look at our list of perfect cubes, 54 is not on that list. So we're going to have to do what we did with the 24, and that's break it up a bit. Okay? So let's narrow this down. We're not going to divide it by 1 because that wouldn't change anything. And it'd be pointless to use anything bigger than 54, so we're going to kind of ignore all of those. So really it's going to be down to 8 or 27. Is 54 divisible by 8 or 27? If you don't know, I mean, it's fine if you don't know, but you can just type it in your calculator and see if it works. Take 54, divide it by 8, divide it by 27, and see if either of them work. If you do 54 divided by 27, you'll see, hey, it works out evenly. You get 2, so we're going to use the two numbers 27 and 2. Okay? 27 times 2 is 54, so that's why it works. All right, when we simplify this, the cube root of 27 is a perfect cube, as we mentioned in number 1. That's just a regular 3. And the cube root of 2, kind of like that 6 in the last slide, is just kind of a remainder. We can't simplify it, so we're going to leave it the same. All right, so there's your simplified answer, 3 cube root of 2. We can do the same process with the cube root of 40. Break up the cube root of 40, because 40 is not a perfect cube, as you can look at the list and see. So we're going to break it up. Again, we're going to repeat this process. We're going to try and find out which perfect cube would divide into 40. We can try 27, but that's not going to work. You can see in your calculator you get some kind of crazy decimal. So we could try dividing it by 8, because 8 is another perfect cube, and that does work, right? That would work with 5. So we're going to use 8 and 5. Now the question, let's simplify the cube root of 8. Obviously 8 is a perfect cube, so it simplifies nicely. The cube root of 8 is 2. And then the cube root of 5, kind of like the last one, is our remainder. And it can't change, it can't be simplified because it's not perfect. And it can't be simplified any more than the way it is. Alright, so that's our final answer today. Alright, and last but not least, we have cube roots of variables. And so there's 2 ways you can go about this. You can go about this using the rule that we mentioned previously, which was n root of a to the m equals a to the m over n. Right, so you can take it from radical form into exponent form. But there's another way which I'll show you as well. So number 4 is pretty easy, especially if you use kind of this method up here. We have the third root of x to the 6th. So we could kind of just follow the same pattern. Then this would be x to the, let's see, 6 is m, so that's going to be our numerator. And 3 is n, so that's going to be our denominator. So it'd be x to the 6 over 3. But of course, 6 over 3 is reducible as a fraction. It's just the same as 6 divided by 3, which is 2. So our answer here is x squared. Right? We can simplify that down to x squared. The other way you can do it, besides using that rule, is write all your x's out. So we have 6 of them because it's x to the 6th power. And then, because we're taking the cube root, we're going to try to find pairs of 3. And I know pairs is not technically the right word for this, but we're going to try to find pairs of 3. So I have all 6 x's here, and I want to group them by 3s. So there's a group of 3, there's another group of 3, and that's all I can make. I don't have any leftover x's, I just have 2 groups of 3, so that's where you get x squared, because 2 is the exponent is basically counting how many groups you have. So if we had 3 groups, it would be x to the 3rd. If we have 4 groups, it would be x to the 4th, etc. We had 2 groups, so it's x to the 2nd power. Alright, so number 5, you can repeat the process either way. If you use the exponent form, like we did in number 4, this would be x to the 9 over 3, y to the 3 over 3, and z to the 6 over 3. But, of course, all of those can reduce. This would just be x to the 3rd, y to the 1st, and z to the 2nd. Alright, so that's if you use the rule outlines here, kind of like I did in number 4. If you want to write them all out, you certainly can. If you have all 9 x's, okay, which, I mean, if you're watching this video in your high school, it's a little bit too many x's, I think, for you to have. But if you have 9 x's, and we want to group them by 3's again, because we're trying to find the perfect cube, or the cube root. So there's one group of 3, there's another group of 3, there's another group of 3. So we have 3 groups of 3. That's, of course, going to be x to the 3rd power, as we've already made a point of. I have 3 y's, so if I write all 3 y's out, and then I try to group them by 3's, I would have one group, so it would be y to the 1st, and then even with my z's, I would have 6 of them, and I'm trying to group them by 3's, so I would have 2 groups, which of course would be z to the 2nd power. So it gets you the same result no matter which way you approach it, but number 6 is a little bit different because there's 2 ways you could potentially write this. I'm going to go ahead and show you both ways. One way is the radical form, kind of like we started off with number 4 and number 5. So this would be a to the 5 over 3, because you're taking the 5 over the 3, the power over the index. The b would be 6 over 3, and then it would be c to the 2 over 3. Which should be simplified to just be a to the 5 over 3, b squared, and then c to the 2 over 3. Simply because for b, 6 divided by 3 is 2. The other way you can do it is kind of like, where you try to find those groups. So if you have 5 a's, all right, and you want to try and group them by 3's again, right, because we're taking the perfect cube root, you would make one group of 3, and you'd have 2 left over. So what this would look like is you'd have a to the 1st power, okay, and then the 2 left over, or 2 remainders, are left inside the cube root. So you'd have a squared inside that cube root, the cube root of a squared. The b's, you can do the same thing. You'll see that it's going to work out nicely because we have 6 of them. You'd make the groups of 3, so you have 1 group, 2 groups, which would make b squared. And then, of course, c's, we have only 2 of them. So since there's only 2 of them, I can't make any groups of 3. So these are left as remainders, and so they're going to be stuck underneath the cube root still. We couldn't take any of them out. It's just going to be c squared still inside the cube root. Alright, so I've got my answer, but it's in pieces, so let's put all of this together. We'll have everything that's not inside the radical, so I have an a to the 1st power and a b squared. Those things are not inside the radicals. And then inside the cube root, inside the radicals, I have a squared, and I also have c squared. So this is the same thing as this. There are 2 different ways of writing it. Both are technically correct ways of writing it. So, I'm going to go ahead and show you both because I don't know how we're going to necessarily need it in the future. But there it is. All right, I'm going to cut the video off here. So I will see you guys in a little bit. All right, catch you later.